If the current crisis has taught me anything yet, then that our economical system is incredibly vulnerable to disruptions of any kind. Global travel and trade allow the rapid spread of illnesses that might have otherwise had a much smaller impact. And even if this situation would just blow over, which it probably won't, who says there won't be another pandemic in 3 years from now? Millions have lost their jobs all over the world in just a few weeks, and here in the West, many now realize that their skills and job training do not allow them to just switch to another job, because together with globalization, job over-specialization has made us less resilient to disruptions than we ever might have been before. In earlier times, a farmer would work in the forest or in a quarry come winter time. That is not the world we live in anymore. The world we live in is the one where your tax accountant has outsourced writing invoices to another company. Will a world of clerks, advisors and consultants be able to pull itself up by its bootstraps? Where will the accountant of the accountant work come winter time? Why am I even talking about this? Well, because this channel is and always has been about learning basic skills and about helping yourself by using your hands and your head. So once again, follow me along as I pick through other people's leftovers at the scrapyards, see if we can make use of things that others have deemed worthless. What do we have here then? Looks like the parts of an elevator. I'm sure these pulleys would have been incredibly expensive at one point. Unfortunately, I'm still lacking the house to install an elevator in. What is this though? Looks like a special kind of oven that I've been looking for. It's coming with me. I'm often amazed by the size of some of the parts that you can find in these places, but in this case I also have no idea what it is. Here's a small cast iron pot, and I have an idea what to do with this. These pieces of thick steel bar here are actually pretty interesting to make stuff on the lathe. Maybe I'll take a few. In this box here I found a number of cast iron weights and a beautiful old vise, and I'll buy that one as well. This decommissioned machine here has huge gears and a number of interesting hydraulic components. Unfortunately, I can't assemble it right here right now. But under this pile of trash, I found something special. A huge Pops brand blower. A very expensive part. This one I'll buy as well. Let's take a look at this little oven then. Any idea what it's good for? Well, it's typically used as an enameling kiln. To access the chamber inside, you tilt this little door open. The purpose of the circular hole in the door is to insert a temperature probe. For example, of a temperature regulator like this one here. Just before I found this kiln here at a scrapyard, I had actually bought a used one. The unit I bought was made by the German company Horst Uhlig. Its name is Uhlig U15, and it's almost identical to the unit I found at the scrapyard. A new kiln like this is usually between 300 and 400 euros, by the way, and I guess it can't hurt to have two of them. Well, we'll have to test this kiln, but I'm actually just starting to get into enameling, so let's find another way to test this oven. Maybe by melting metal? I'm connecting the oven to the workbench I recently bought, where we're using the built-in power meter to measure its power consumption and input current. I'm placing the temperature probe of the Fluke 875 DMM into that little hole in the door, and the kiln does indeed start to heat up. We operate the kiln without a temperature regulator or controller, which is not recommended. However, the kiln is going to heat up and it is eventually going to stabilize at a maximum temperature. We're just not able to regulate that temperature. Let's melt some metal then, and I will start with tin because of its low melting point. I place some old solder wire onto this stainless steel tray. It should be noted for safety reasons that this wire also contains lead. After some minutes, the solder has already melted. A dark reddish glow can be seen emanating from the walls of the chamber. The brown residue comes from the flux inside the solder wire. And since I don't have a real mold at hand, let's pour the tin lead alloy onto a coin and see if we can make a negative of its surface. Nah, that wasn't enough. Let's add more solder and try it again. Another fail, obviously. For the next try, I want to use even more solder. But I need a better smelting pot than that totally improvised piece of stainless steel. Here comes this little cast iron pan we found into play. It would fit just perfectly inside the chamber if it weren't for that handle. So let's cut it off then. The smoke coming from the kiln is also from the flux inside the solder, by the way. And there you go. The negative is that of a token that I bought on a recent sightseeing trip. So far so good, but tin starts melting at only around 230 degrees Celsius and lead around 330 degrees. What about something that needs a much higher temperature to melt? I have now inserted a piece of aluminium into that pot. The melting point of aluminium is at 660 degrees Celsius. After a few minutes, the cast iron pot is already glowing faintly. The aluminium has already gotten more malleable, but is not yet melted. Again, a few minutes later, the inside of the kiln is emanating a bright orange color. The iron pot is cherry red, and the aluminium has molten. And here is the little ingot that I have cast. Can we go higher though? Here's a piece of brass scrap. No, it's not ammunition, even though it might look like it. It's just an old piece of brass tubing. Brass is an alloy composed mainly of copper and zinc, and its melting point is typically between 900 and 940 degrees Celsius. After a few more minutes, the cast iron smelting pot is now glowing orange. The brass is also glowing in a reddish orange, but has not yet molten, though it has gotten really soft. And I have now inserted these brass screws here into the pot to see if smaller parts might actually melt. And this time the smelting pot is glowing at an even higher temperature and even brighter orange, but the little screws have not molten. Maybe it's just not hot enough for brass to melt. Maybe this kiln could also be used for annealing and even forging small workpieces of steel though. I'm now placing a piece of steel into the chamber. And after a few minutes the piece is red hot and can easily be bent in the post vise. This kiln might just be powerful enough to be used for forging small knives. The kiln and the cast iron pot in combination were a really lucky find. Let's go on to something much more challenging then. Let's take care of this old vise then. And old it is. I can't tell when exactly, but I'm sure it was made before the Second World War. Maybe we will find hints. It has rust all over the surface, and whatever paint job it might have had at one point is gone. The jaws appear to be detachable, and for their age they are in incredibly good shape. The crank can still be turned quite easily as well, but it has one major fault, and that is hidden under this steel angle plate here that was bolted to the cast iron body of the vise a long time ago as a repair measure. On the other side it has also a logo that is yet unknown to me though. I'm applying some WD-40 and I turn the crank until I can take the entire spindle out and push the movable jaw off the vise. And because I frankly can't stand to look at the dirt and the old cobwebs, I do some cleaning right away. To take out the crank, I also unbolt this little U-shaped retaining plate here. At least one of the two screws is not original and bent out of shape. But what about the major damage that I'm suspecting to find under that old steel angle plate? Well, let's find out. After removing the nuts, I can punch out those bolts, and what we find is one major crack. 3 holes were drilled through the remaining cast iron sidewall to attach a steel plate here. Under the dirt we find remains of an old green paint job and the word Eikar, spelled E-I-K-A-R. After some online research I found a picture of some old vises, two of which, the upper and the lower one here, are of the same make, as can be seen by comparing this logo to the one on our Vise. The name Eikar is apparently the name of the model of this particular Vise, while the name of the company is Breitenfeld und Scholz, from a city called Bunzlau. I found this information through some online research inside this Arbeitsbuch, workbook, a document handed to German workers during World War II. The city of Bunzlau was located in Silesia, or Schlesien, as we would pronounce it in German. Back then it was in Germany, today belonging to Poland, and with a Polish name, which I better won't try to pronounce. Maybe some of the Polish viewers can help me out here, so please leave a comment in the comment section below. And since the Germans in that town would have been displaced at the end of the war, it is certain to say that the Vise was at least made before the end of World War II. The model in the bottom of this picture seems to be the same model we have here, and it also has a similar problem. A piece of the cast has broken off in the same place and was fixed with a steel angle piece. We will attempt to repair this vise with another brazing job. Before I will do that though, let me remove the rust and grease from all the surfaces by wire wheeling them off. Usually I do that with my large Bosch angle grinder, but this time I'm trying it with a smaller wire wheel and a much lighter angle grinder. It is probably much less tiring for the arms. Fortunately, removing the rust and dirt has not revealed any further major damage. In order to fix this vise, I will make a new replacement for the old broken off feet. I will make that from this angle piece and some flat stock. Since the remaining cast here on this side has also been weakened by those 3 drill holes, I will cut out a large rectangular piece so that I will be able to fit the angle piece in here and have a nice straight form for the brace. I take away material in all places where the original casting has cracked. And I do that with a cutting wheel that indeed cuts through the material like butter. And before making the replacement part, I grind angles into the edges. Here a channel will be formed for the brass to flow into. After the angle piece has been cut to length, it is held against the still original side of the vise and its outline is traced onto that piece of stock. After cutting the piece into a rough shape with the angle grinder, these 2 pieces of flat stock are placed onto it and TIG welded in place as reinforcements. Eventually, a grinding wheel is used to give the new piece a rounder shape and also to work an angle into the edges, just like we did with the cast iron side before. We can now check if the 2 parts fit together, and indeed they do. The opposing angled edges form a channel. On the lower part, air gaps of around 5 mm between steel and cast iron are supposed to allow for a thick enough brass seam to hold the parts firmly together. But first, new mounting holes will have to be drilled. To mark the correct spots, I use the hand vise from an earlier episode to clamp the 2 bottom pieces together. Not its original purpose, of course, but it's always nice when tools we repaired in earlier episodes come back to help us. And you can find links to the other 12 episodes I already made in this series down in the video description, by the way. And with this replacement section finished, it is time for the real deal, the brazing job. In the last episode of the series, I had built this coal-fired forge from an old brake drum, a blower, and other parts I found on the scrapyards. We will now use it to preheat the cast iron body of the vise for brazing. At first, a small fire is supposed to heat up the workpiece rather slowly, and we let it burn for a few minutes. I also move the vise around a little bit so that a more even heating is made possible. The replacement foot has been temporarily fastened in place with 2 pieces of steel and some bolts. Now, coal is added to the fire and the blower is activated. I eventually turn the vise around so that the bottom side, where we will actually perform the braze, is heated up properly. With some pretty big pliers, I bring it over to the outside workbench. And the brazing process begins. In the brazing process I use an oxy-acetylene torch, in German Autogenschweißgerät, to braze or hard solder the cast iron and steel together. Brazing is traditionally used to repair cast iron workpieces because the temperatures in brazing are lower than with welding, and thus the stress on the workpiece is also lower. The brass is capable to create a strong bond between the mild steel and the cast iron on the other side, but thorough preparation of the braze is necessary. Preheating as well as slow cooling down after brazing is important. What looks easy enough in the videos, by the way, is very hard in reality. I wear fireproof clothing, thick gloves, a face mask, and the torch becomes very heavy in your hands while the massive workpiece emanates enormous amounts of heat. By the way, don't be fooled by the fact that everything happens so rapidly in these videos. In reality, everything takes much longer. My Repair-A-Thon videos here, for example, are between 15 and 30 minutes long as a finished product, but every single one so far required more than 100 hours of physical work, filming, editing, texting and audio recording, and I mean for each episode, not for all of them together. For the workpiece to cool down slowly, it is again placed on the forge that still radiates a lot of heat, and a welding blanket is placed on top until the next morning. With the vise cooled down, the temporary fasteners are removed and the surface is cleaned with a WD-40 and some steel wool. The brazing slag is removed with a welding hammer, and the surface of the vise is wire wheeled off once again. Now I can inspect my braze for the first time. Even though it might look a little rough here and there, I'm pretty proud of it. This is only my second attempt at this on a large workpiece like this, and the brass has made a good connection with both iron and steel everywhere, and I was even able to bridge those 5mm air gaps very well in my opinion. The parts of the vise are finally oiled, the retaining plate installed, and everything is put back together. The vise is now installed on my workbench, and I guess you'll see it again in future projects. Here is the big blower we found. It weighs around 13 kilograms and is made from cast aluminium, and according to the nameplate it was made by the German company Papst. 860 watts is a lot of power for a blower like this. And if you Google the part number, you will see that it was made for a type of gas heating system, and that this part is prohibitively expensive. Upon removing the plastic cover, we find a massive brushless DC motor. This one is one of the biggest BLDCs that I have ever found in anything from the trash. Nothing in here looks damaged, and indeed the unit only appears to be a few years old. On the PCB we find two connectors, one of which is just a power connector for the mains that I could identify rather quickly. And since I don't have the connector, I simply soldered a power cord to it temporarily. It's awesome to see this blower apparently blasting at its full power, but for real-life applications it would be better if I were able to control the motor speed. This 5-pin connector here probably has a PWM input. Online I found a datasheet for a similar blower. Unfortunately, the datasheet lists 8 different types of interfaces for Pabst blowers, and the pinout just doesn't match what I found here. Maybe this was built to different specifications for a particular customer. But after a lot of probing around, I think that I have found the PWM pin, and I connected it to an Arduino. And indeed, I'm now able to control the motor speed. The program that I've been using here, and this is about as simple as it gets when it comes to programming the Arduino or any microcontroller board for that matter. So what really happens here is that you first declare pin number 3 as an output pin, and then you switch that pin on to the high state, which means plus 5 volts in this case. Then you wait 250 microseconds, and then you pull that same pin down to low, again wait 250 microseconds, and then the loop starts anew. This is basically a way of building a pulse width modulation manually, while a lot of you probably know that the Arduino actually has a built-in PWM function, and that you can use that by using the command line analog write, not digital write. But the problem with the analog write is that it uses a fixed switching frequency, and the thing here is that the datasheet stated that you have to have a switching frequency between 2 and 6 kilohertz. Well, that is not within that range. So what I've been doing here is to manually set the frequency, and the frequency f equals 1 over capital T, and capital T is the on plus the off time. So capital T is 500 microseconds. The switching frequency is then 1 over 500 microseconds, and that's 2 kilohertz. Now, changing the duty cycle, meaning if the PWM is lower or higher, is done by changing these values, while T always stays the same, 500. So for example, you could have, in this case it's 250, 250 means that you have 50% duty cycle because it's switched on 50% of the time. If you would say have it on for 400 microseconds and then off for 100 microseconds, that would be 80% or 0.8 duty cycle. And well, this is just a very small lesson really, but a very useful one. So it appears that there just isn't anything to fix with this blower, and it baffles me that it was thrown away. However, it might come in handy in a future build, and we will then take a closer look at it. That's it with today's finds, but another Repair-A-Thon is already in the making. So if you liked this video and would like to see more of it, then please let me know and give the video a like. If you want to aid in the future production of videos, you can also become a supporter on Patreon under patreon.com/tpai, or make a donation via PayPal, address down in the description. See you soon, guys.